The next topic is base theorem, and it's really a very interesting and important topic. So let's begin with it. Okay. When we are finding the overall probability of a event PA, it is difficult to compute it directly. And law of total probability partitions the sample space into exhaustive and non-overlapping scenarios. So we can get the value of probability of A with that. But what is the role of Bayes theorem? It provides like law of total probability provides the denominator, the marginal likelihood or the normalizer in the Bayes theorem. It plays like that. Now, what it actually means, uh, let's go forward and I'll tell you from the slides. Okay, so here we observe an effect and want to reason back its cause. What law of total probability do is like it goes forward. It knows the causes and it finds the probability of effect. And what Bayes theorem do? It goes backward. It observes the effect and find the probability of the cause. Okay, so prior belief plus likelihood of evidence gives up the updated posterior belief. Okay, so in most of the most important single equation in statistics and ML, so it's very important. Now, if we move on, and this is the formula of uh, what we say, like this is the formula of Bayes theorem, and this term like probability of BI is here. It means prior. Then there is next term likelihood, which means huh, which means A given BI. This is the likelihood. And likelihood means how probable is evidence A if BI is true. Then comes marginal likelihood, which is probability of A, means total probability of the evidence. It is a normalizer, okay? And here is posterior, means the updated belief in BI after seeing the A. Okay, so posterior is directly proportional to likelihood into prior. We can get this from the formula. Next thing is that marginal likelihood grounds the updated belief in reality. Okay, this is all about the formula only. Now, this is the derivation how that formula came from the conditional probability formula. Just put the value and get the formula. Simple. Now, okay. So this diagram simply states that the new evidence, the new uh, the new prior value will be the equal to the posterior value of the previous step. Okay, the order in which evidence is processed does not matter. The final belief will remain mathematically identical. Okay, now moving on forward, it is just the sequential updating process is shown here. Okay, see, here's the prior, here's the posterior. This posterior will become the prior for this next step. Okay, moving on forward, this is just an example. And some of the, okay, these are the traps like where we can make mistakes in Bayesian formula questions. So first is base rate neglect, like medical test sample. There was a question given in the slide only, which shows that medical test example above. So human consistently ignore the prior and just to trust the likelihood. This is one of the well documented cognitive bias. Like always ask how rare is this in the population. Okay. Second thing is like prosecutor's fallacy, means probability of evidence given that innocent is not equals to probability of innocent given that evidence. Okay. Next thing is likelihood is not the posterior. Means probability of data given hypothesis does high does not mean that probability of hypothesis given data is also high. You need the prior and normalizer too. So this is where intuition breaks in MLE maximums like maximizes likelihood, not the posterior. Okay. Now the next step is that probability of A in the denominator is same A as in the numerator. But we make mistakes sometimes that we compute probability of A incorrectly, but by not using LTP properly, the denominator must account for all always. So A can occur across the full partition. Next thing is like uninformative priors are not natural. So choosing a flat prior means it constantly looks uninformative. But if you are reparameterize, like what you do, use theta square instead of theta. The flat prior on theta induces a non-flat prior on theta square. So this is there is no truly uninformative prior in general. So there is one thing called as Jeffrey's prior. It is an attempt to handle this. Okay, so remember it. Now, independence of sequential observation. The sequential updating above assumed each test result is independent, even the disease status, if tests are correlated. So, you cannot update this way. Okay. Now, why we are studying this? What is the ML connection of this? So, in the MAP estimation, we use Bayes theorem like maximum A uh, posterior is equals to argument max of probability of theta given data, and it's equals to arg max of probability of data given theta into probability of theta. So it is just Bayes theorem with the normalizer dropped. Since it does not affect the argument max, so L2 regularization is equals to Gaussian prior on the on this weights. Okay. Then next thing is naive Bayes classifier. Like it directly applies Bayes to compute probability of class given the features. Okay. Now next thing is Bayesian neural networks. It maintains a full posterior over weights like probability of theta given data instead of a point estimate. Okay. Next, there will be topic like last of the topics which we will cover in the playlist. The names I will tell you now, like MCMC and variational inference. They both are methods to approximate the posterior when like probability of theta given data when it is interactable, which is it almost always like which is almost needed in deep learning. So that's all for this video. I explained well from my side, and I hope like you liked it. And if you find any mistakes, just you can say me in the comments. Thank you. Bye bye.